Hey guys, just back again trying to solve the questions on the Art of Electronics, Chapter 2. I did solve the first question on my previous video and demonstrated its the actual design on a breadboard and tested it and it worked. Now we'll try to solve question 2 on how to use transistors in practical applications. That is basically taking properties of transistors in the actual world where their non-ideal behavior comes into play. So basically this question will help us to understand the non-idealities concerned with using transistors in practical applications. And this includes temperature, variations in beta of a transistor, and as well variations in the output impedance of a transistor and how that affects circuit performance. So let's go ahead and solve this question. This question is a little bit mathematical oriented, so but it's the nature of using transistors in real applications, so you have to do a bit of math to deal with these kinds of issues. So don't get discouraged if solving this question is too mathematical. But this is very important because it helps you use the transistors properly. So let's go ahead and read the whole question, and it has about 4 parts, and we'll do each part consecutively and hopefully solve it properly. Okay, so the question says, consider the current source in figure 2.79. And the current source we're talking about is basically here, as you can see. Let's go back one more page. So the current source you're talking about is this simple common emitter amplifier, and it's used as a current source to sink current from the load to ground. So as we have seen the diagram, or the circuit diagram for it, let's go back and reread the question. So now we know what that the circuit diagram looks like. The first part of the question is, what is I load? So basically it's asking us what is the actual current through the load based on the biasing of the transistors as shown in the diagram. So basically what I will do is I will solve that as accurately as possible. I'm not gonna go use the voltage divider rule to directly find the base voltage. Instead, I will take into account the base current. Okay, I will demonstrate that in a second. So here is the setup. Basically, the load as shown is here, and there's a transistor, and the given beta for the transistor is 100, and also the base voltage given for this is the VBE. I mean, the VBE drop of the transistor, VBE, is given as 0.6 in the question. So we'll use this to solve the base voltage. So what he wants us to solve is the current flowing through this branch here, so passing through the load. And in order to do that, we have to find the base voltage. So we call this VB, and we're going to call this IB. Usually what you could do is you could just take, as mentioned earlier, you could just do a voltage divider rule and find the base voltage, because we know our supply voltage, and ignore a base current and solve it. But I don't like to use that method. I want to remain as accurate as possible, so I will consider the base voltage. And it's very easy. All you have to do is write the KCL at this point, which is basically it takes into account of the current flowing on all these 3 branches here, and that will give you as accurate solution as possible instead of ignoring the base current. So I will take into account the base current when I'm solving this. Okay, so let's write the KCL at that point to find base current, and if we know base current, then we also know the current going here, because the relationship between base current and the current in the collector is a factor of beta. So if we know base current, then we know the current going through the load. So the equation at the KCL equation at this is VB minus 10 volts divided by 8.2k ohms. That's the current flowing in this path here, and the other path is VB divided by 1.6. So VB divided by 1.6k, and also the current flowing on this branch, which is IB. And since that's a node, and due to KCL law, this should add up to 0. So put that properly right here. So that's the first equation. So we'll call this equation 1. And equation 2 is relating the output side of the transistor. So basically the emitter current in relation to this. So basically what we'll do is we'll write a KVL in this loop here. So if we do that, we'll start with VB. So minus VB plus the base emitter drop, which is given as 0.6, but I'll write it as VBE, or I'll just write it as 0.6. So yeah, so 0.6 volts plus the current flowing here multiplied by the 1.5k resistor gives us the drop across the emitter VE, basically the emitter voltage, and that is beta plus 1 multiplied by IB, because the relationship between emitter current and the base current is beta plus 1. So beta plus 1 IB multiplied by 1.5k equals 0. So now you have two equations, two unknowns. The two unknowns are the base voltage VB and IB, and you know beta. So just plug this into your favorite simultaneous equation solver, or you know, do it by hand. It's very simple. So if you do that, you will get VB to be 1.624 volts and IB to be 6.756 microamp. And since we know IC is beta times IB, then IC becomes 675.6 microamp. Therefore, the current, the constant current passing through the load, basically, which equates to the collector current we just found, is 675.6 microamps. So that's the solution for the A part of the question. Okay, now let's go ahead and solve the B part. The B part says if HFE varies from 50 to 100 for a collector voltages within the output compliance range. Oh, sorry, I skipped actually there's a second part of A. It says actually, what is the output compliance? Assume VB equals 0.6, which we already know. And basically, the output compliance of a current source is the voltage necessary for the collector emitter voltage to vary in order to maintain the constant current. So basically, the transistor, if I illustrate on the diagram here, sorry for not focusing fast enough, but yeah, so the current, the output compliance is defined as the collector to voltage emitter variations, so we'll call it delta VCE, necessary to maintain the current constant in the load. So if you attach, say, 1 kilo ohm load, the current that passes through it will still be what we found here. But if you were to attach on a, let's say, a 10 kilo ohm, the current is going to be that much as well, but the voltage will be different, and that is related to the change in VCE. And that change in VCE, to maintain the current constant through the load, is called the compliance voltage. And if the transistor cannot maintain the compliance voltage, then the transistor goes into saturation. Then you don't have the nice relationship between IB and IC, which is beta. So basically, so that's what the compliance voltage is. So to find the compliance voltage, all we need to know is the point that this collector goes so where VCE goes into saturation, the transistor goes into saturation, and the transistor goes into saturation where the collector voltage is about 0.2 to 0.3 volts above the emitter. So all we need to know is now find out the voltage here, which we already did, because we know VB minus 0.6 gives us the emitter voltage. So I'm going to call that VE is VB minus VBE, right? So VB we have already found it as 1.624 minus 0.6. It gives us 1.024 volts. And we already know, so basically that's the voltage that will remain here as long as there's that constant current flowing here. So the transistor will go into saturation at VCE plus VE, and VCE is 0.3 plus the VE we already know 1.024. Therefore this will be 1.324. So the moment the transistor gets into saturation, the collector voltage, so VC, we'll call this VC, so VC equals 1.324 volts. Now the compliance voltage, going back up to here, is, we know the collector when the transistor is almost off is 10 volts minus right before it enters saturation, which is 1.324, and this gives us basically 8.676 volts. So this is the compliance voltage. So the transistor will maintain its constant current in the range between 0 volts, well, yeah, almost 0 volts to 8.67 volts. So basically that's the compliance voltage. As long as we put a load that can only vary between 0 and 8.67 volts when we insert it here, insert it in this branch here, then the transistor will remain as a current source. So that's called the compliance voltage. So we have completely solved the A part. So now let's go to the B part. So I'll read the B part of the question. Let's find the actual page in the book. There it is. The B part says, if HFE varies from 50 to 100 for collector voltages within the output compliance range, how much will the output current vary? It says there are two effects here, so we'll describe the two effects affecting this this transistor current source when basically the HFE varies from 50 to 100 for a collector voltage within the output compliance range. So what we'll have to do basically is we just need to recalculate. We already know at beta of 100 what the current is, the constant current, which is IC, but all we have to do now is recalculate this equation. Instead of using a beta of 100, so we use 50. So basically we just need to change this factor here to 51. So if we change that to 51 and recalculate, we'll get a new VB, and we get a new IB, and also we get a new IC. So let's redo that and come up with a solution. So basically plug in these two simultaneous equations to your favorite solver. You can use a calculator or do it by hand and come up with a solution with a beta of 50. a beta of 50, which is beta plus 1 for the IE in relation to IB gives us. So let's go ahead and do that. Therefore, we get VB equals 1.615 volts, and IB changes from 6.75 microamp to 13.27 microamp. It almost doubles for a change of basically a change of 50 in beta. And IC goes from 675.6 microamp to 676.8 microamp. So as you can see, the change is quite minimal actually. The change in beta, which is a factor of 50, or actually a factor of 2 to be exact, sorry, because it changed it from 100 to 50, so a factor of half actually. So if you put a transistor that has a lower beta of 50 instead of 100 into this circuit, the collector current is going to only change by almost, how much is that? That's almost a microamp, basically, a little over a microamp. Just 1 microamp, as you can see. And the reason is this biasing scheme is very, very stable stable. It's basically, it doesn't depend on beta. Reason is because when you look into the transistor from here, the amount of current that goes into the base of the transistor compared to the current that flows through here is negligible. So this is very good biasing. Basically, if you want to put it into a technical term, this is called stiff biasing, because the draw of IB, the current that goes in here, doesn't really affect the voltage here. It doesn't really drop by much by touching this transistor here, whether it has a beta of 100 or a beta of 50, as you can see. So always, when you're designing a transistor, biasing a transistor, you always need to use stiff biasing so that you can avoid the biasing being dependent on beta. So this is very good biasing. And another way to check is also looking at this. The input impedance in the transistor is beta plus 1 times 1.5k. So let's say beta, let's approximate it to beta multiplied by 1.5k. So if you have a beta of 100, then this is basically looking into here, it looks 150k. It doesn't look 1.5. It looks 150k, as if we're looking at 150k. Therefore, and if you parallel these two to get the base resistance here, compared to 150, the parallel combination, this is very small. So really, this section doesn't load, this biasing section. So this is a very good way to bias. And as you can see, recalculating it for a different beta, it proves that it's a good biasing. So that's part B, and this is within the compliance range, as you can see. Going back to the question, it says at the end of the B part of question 2, how much will the output current vary? So we've proven that it varies by around a little over a microamp. And it says at the end, there are 2 effects here. So the 2 effects here are, one effect is, of course, due to the variation of beta, then the current will change. And also the other effect is the variation in the collector to base change in voltage, because when the output compliance is from 0 to 6.7 volts, when you're changing the load within that compliance range, the collector to base junction is not going to remain the same, the voltage. So basically that will also affect the current that goes here through here. So as you can see, this change of about 1.2 microamp not only is because of the beta change, but also the collector to base voltage. And that collector to base voltage manifests itself as the output impedance of the transistor. So basically, if you see the transistor curve, normally it will go up like this in the saturation region, and then it will flatten like this, but it really doesn't flatten like this. It actually goes like this. So as you can see, it doesn't go flat like this. So there is a slope related to that, and that slope is the output impedance of the transistor, this being VCE, and this being IC. So that output impedance is actually related to the change in the collector to base voltage, and that also relates to the internal structure of the transistor, and it's called the early effect. Actually, basically when the current passes through here and there's a change in that current due to that compliance change, that compliance voltage change here, the collector to base junction, actually its width will increase and decrease, and that width increase and increase is manifested as the output impedance of the transistor. So that's the other effect. So the two effects are the beta change and also the early effect. Those are the two effects that the book is talking about, and these two are very important. Okay, part C says, now we'll come to the actual early effect, how it affects the current source. If VBE varies according to VBE, delta VBE equals minus 0.0001 delta VCE, the early effect, how much will the load current vary over the compliance range? So basically now what we need to do is, basically it's asking us how does the early effect affect this, and it's giving us a relationship between the base voltage and the collector voltage, collector to emitter voltage, the base to emitter voltage and the collector to emitter voltage, and that relationship is the minus 0.0001 voltage change in VCE. So what we'll do is we'll take into account this change into our calculation. So let's set that up and recalculate and find out how this affects the load current. Okay, so let's start with this relationship here. And we know that this delta VCE is actually the compliance range. It's going to vary from 0 to, as we calculated earlier, 8.676 volts. So if we calculate the change in base voltage due to the early effect using this relationship, it's going to be minus 0.0001. That delta VCE is actually the compliance range, which we calculated earlier. As you can see, it's this change. It's basically this, as we said, right, that change in compliance voltage is actually manifested itself as the early effect, and we're given that this is the relationship with the delta VBE. So if we put that in volts, and we're gonna get we're gonna get this number, and that number is minus 867.6 microvolt. So and during basically this change in compliance voltage from 0 all the way to 8.676 will affect VBE by minus 867.6 microvolt basically. So now what we have to do is we need to recalculate again the load current, and I will give you, instead of going back to that whole equation, we can use this equation again, assuming beta of 100. We can put now, instead of putting minus 0.6 volts here, we're gonna have to add that effect that we just witnessed. So the voltage is gonna rise from 0.6 minus that additional 867.6 microvolt, sorry, 8.67 volt. Instead of using that equation, we'll use another equation which we can derive easily, basically by the relationship here between IE and IB and IC. Basically that equation is IC equals beta over beta plus 1 divided by V base minus VBE divided by RE, RE being the emitter resistor. And this is very easy to derive. I don't think you need an actual derivation to do this, an actual derivation for me to do. But if you want, I could quickly show you the actual derivation I made earlier. So if I get that derivation, just to give you an idea of how that derivation comes, it's very easy. So all you do is basically, it's really not that difficult to derive it. So I'll just put it in the shot for you to take a look. So just take a look. This is the actual process. I start with IC equals IE minus IB, and I replace what IE is and what IB is, and just do some manipulations, and I end up with that equation. So you can go ahead and pause this and take a look at that derivation. So let's go ahead and solve this now. And we know beta is 100 divided by 101. We know VB 1.6. Just refer to the earlier solution. This is at beta of 100, 24 minus. Now VBE is going to change from 0.6 minus 867.6 microvolts, and then we're going to divide that by 1.6k, as you can see. So all we do is now we'll get our new IC from here due to the new change in early effect. Basically, the early effect in that compliance range will have our VB will change from 0.6 to that. So we need to include that here. So if we do this calculation quickly, and I'll give you an answer in a moment. Okay, so the answer is 676.48 microamp. And note that there should be a bracket here, because the relationship is as the compliance voltage increases, there's a decrease in VBE because of this minus sign. So remember to include a bracket sign here to account for the change in the compliance voltage that has an effect on VBE. So you do that calculation, you get 676.48 microamp. And the original that we calculated was 675.6 microamp. So as you can see, it's also a little over microamp. So the effect is also negligible here, because our compliance range is not that much. If our supply voltage was large, say 40 volts here, then since we're going to have a huge change in delta VCE because of this relationship, then our change in current due to the compliance voltage changing will be quite substantial, a lot worse, certainly a lot worse in this case. But in this case, since our compliance voltage is just 8.676 volts, due to our supply voltage being not a lot, just only 10 volts. So if you see if we can focus here. Yeah, then the effect is actually not pronounced. The early effect is not pronounced that much. So our output impedance doesn't change by a lot. That's what it all means in the transistor. Okay, now that we have solved part C, let's go to part D. And part D that says, what is the temperature coefficient of output current assuming that HFE does not vary with temperature? So that's the first part. So this one's quite involved, but the actual derivation involves quite a bit of calculus, so I'm not going to go through it here. But in the book, it's given the actual change in voltage of VBE due to temperature change is given by this relationship, which I will just give you. And if you want an actual derivation of it, you can Google it and you'll get the actual derivation. But so the partial derivative of VBE with respect to temperature is actually minus 2.2 millivolts per degree C. So as you can see, for a degree of change, for 1 degree of change, we'll have a drop in VBE by 2.2 millivolts. So if the temperature increased, say, in 10 degrees, then definitely we'll have quite a bit of change. So we'll have a 22 millivolts of change. Basically, the VBE will drop from 0.6 by 22 millivolts. So this is the actual answer for it. So I'm not going to provide the actual derivation here. And now we'll continue and solve the last part of part D. The last part of part D says, what is the temperature coefficient of the output current assuming that HFE increases from its nominal value of 100 by 0.4% per degree C. So we'll go ahead and solve that. Actually, sorry, we're not gonna go ahead and do the last part of it. We'll continue actually solving the first part of part D, because he wasn't the question wasn't asking the temperature coefficient of the base emitter voltage. It's actually asking the temperature coefficient of the current in the circuit. So basically it's asking delta IC delta T. This is what it's asking actually, so my bad. So I will continue to solve this part. All we have to do is basically to go back to this equation and integrate differentiate IC with respect to time, with respect to temperature, and find the expression for that and plug in our values, and we'll get the temperature coefficient of the current, that's the load current in the circuit. So this should be very easy. So we'll go ahead and solve that part. So since IC equals beta divided by beta plus 1 into VB minus VB divided by RE, this term is actually called alpha. Alpha being tells you the relationship between IC and IE. Basically IC equals alpha multiplied by IE, and alpha is normally less than 1, and you can see why, because normally, because of this term, alpha is basically less than 1, so normally close to 0.99 something. So in this case, the equation becomes, the above equation becomes alpha multiplied by VB minus VBE divided by RE. And since we are guaranteed that HFE will remain constant, which means alpha will remain constant, so let's distribute this. Alpha times VB divided by RE minus alpha VBE divided by RE. So now we're going to take the derivative, basically the partial derivative with respect to temperature of the current. So delta IC delta T is, this term is all constant. Since we are guaranteed that HFE will remain constant, it's constant. This term is constant because it's the base voltage, it's fixed by the voltage divider. This is a resistor, so it's constant. So when we derive it with respect to temperature, this term goes to 0. So all we're left is with this part. So we get minus alpha multiplied by delta VBE delta T divided by RE. This is the derivative of the base emitter voltage with respect to time, and we with respect to temperature. So this term we already know, like I said, it's given here. It's a lengthy derivation to get it with actually from the Ebersmall relationship between IC and VBE. So with this term here, ICO E VBE divided by VT minus 1. So from this you can deduce this if you do actual some calculations.